Hey, College Algebra class. We're going to be starting a new chapter in Chapter 3, and the first thing we're going to be looking at is Section 3.1, and this whole chapter is about polynomials. The first thing we're going to be looking at is quadratic functions before we get into anything, any polynomial that's bigger. So, first thing is we're going to be looking what is the quadratic function, and then looking at graphing techniques, just like in the previous chapter. We're going to be graphing quadratics just like that. And then and completing the square. We've looked at completing the square before to find zeros, but we're going to be looking at that to help us in putting our quadratic in something called vertex form. And then we have the vertex formula that we're going to be looking at, and then we're going to look at a quadratic model. Here is the definition of our polynomial function. And a polynomial function f of degree n, where n is a non-negative integer, is given by this right here. And I know that looks kind of big and scary, but it's really not. I'll give you some examples of what polynomials really look like. But this just encompasses all polynomials, where you see this value right here, a sub n, and then a sub n minus 1, and then so on. It keeps on going down until we get here to our constant variable, or sorry, not variable, just our constant. What those are they're known as coefficients on our variables of x. And then our variables of x, they are raised to powers. And like I said here, n is a non-negative integer. That's what meets the definition of a polynomial. Our values of n cannot be negative, and also they cannot be fractions. Okay? Well, yeah, they can't be fractions. So let's look at some examples. Here you go. Here's some examples of polynomial functions. We start out with the constant. So f of x equals just some number. And then we go to the linear equation. Well, right there, f of x equals 5x minus 1. There's an example of a linear function. We've looked at linear functions before. And we've also looked at some quadratic functions before in the previous chapter whenever we went to graph some. But here is a quadratic function with our value of our degree here is 2. And our leading coefficient here is 4. So these two things are kind of important, the degree and the leading coefficient. Need to be able to recognize those two things. The degree is always going to be the highest power that you see on x, and then the leading coefficient is going to come from that term. It's going to be the coefficient that is multiplied to the x term that has the highest degree. So here we have a cubic. Cubic is known with the highest power, or the highest degree, is 3. And then notice the leading coefficient is 2. And then this right here is known as a quartic function, and the degree here, of course, is 4. And the leading coefficient on our x to the 4th term is understood to be 1. So whenever we don't have a number there, it's understood that it's being multiplied by 1. So our leading coefficient is 1. So there are some examples. Now let's look at some other things. Here is our definition of a quadratic function. It is known as f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and our a cannot equal 0. Otherwise, it wouldn't be a quadratic function. Here's the quadratic function in simplest form. It's f of x equals x squared, and that's one of our basic functions that we looked at in the last chapter. And here it is graphed for us. And we should know that the range begins here at the vertex and goes upwards. or depending on the direction of our quadratic function, whether it opens up or down. And that's how we're going to find the range. We're going to look at the vertex and then either go up or start negative infinity and go up to the vertex. And then domain is always going to be all real numbers. All right, here's some facts about parabolas. Parabolas are symmetric with respect to a line, and that line is called the axis of symmetry, or just the axis. And the point where the axis intersects the parabola, so this point down here, is known as the vertex. So like I said in the previous slide, your quadratic equations, they can open up like this one, or they can open down like this one. Alright, so here's applying graphing techniques to a quadratic function. We're going to be using this just a little bit in this section here to help us in graphing some of our quadratic functions. So we should know the majority of this stuff here, except maybe this term right here opens up and opens down. So let's look at that first. This value of a, we know that if it's greater than 1, then it's a vertical stretch. If it's between 0 and 1, it's a vertical shrink. But also, for a quadratic function, this value of a, if it's greater than 0, which is a positive value, it tells us that this quadratic function opens upwards. And then if it's a negative value, like this right here says a is less than 0, then it's going to open down. And then this value of h right here, this value of h is our horizontal shift, and it either moves to the left or to the right. And then this value of k, that is our vertical shift. It opens upwards it doesn't open upwards. It moves up or it moves down. So what we're going to learn is that this value of h and k that we see here, these two values, h and k, that right there is going to help us find where the vertex is, like I showed you in the last chapter. Where h and k are, that is our vertex. That's going to help us in graphing our function. Okay, so remember that. Alright, for this first example, what we're going to be doing is graphing this function given here and comparing it back to the graph of y equals x squared, which is what I previously graphed right here. And we're going to just be using our graphing techniques that we learned in the last chapter, along with knowing that our vertex is going to be at this, our hk value. So let's just write that down. Vertex is at -3, 5. And I'm going to plot that point first. So -3, 5, right here. This is going to tell us right here that the graph is going to open downward, and also there's a vertical stretch on this graph, and our vertex now is here. So it's this, comparing it back to this x squared function, we're going to reflect it across the x-axis and then move the vertex over, or everything over, to the left 3 units and then up 5 units. And what it's going to look like is a much skinnier graph, like that. So there is using our graphing techniques from the previous chapter. Alright, in example 2, we're going to be graphing this function right here. But before we do that, we're going to do something called completing the square of this function. And this right here, whenever we complete the square, it puts it in vertex form. And if you remember, vertex form looks like this. We have a x minus h squared plus k. That right there is vertex form. And whenever we put it in vertex form, it helps us in being able to identify the vertex of our equation, of our function here. So let's get it into vertex form by completing the square. And if you can't remember completing the square, I'll show you step by step in this example. So it's a little bit different than whenever we are completing the square of an equation than compared to completing the square for a function. So what I'm going to do is say put the first two terms in the set of parentheses just like this, leave a little bit of space, and then on the outside put your constant, so -5, and then also we're going to put a number here. What number goes in those blanks is it's going to come from your value, your coefficient on your x term. You're going to say take that x term, divide it by 2, and then square it. So whatever that term is, or that coefficient is, divide it by 2, square it, and that's the number that is going to go in each of these blanks. For the first one, we're always going to add that number, and that number is 1. And in the second one, we're going to subtract that number. So now, what we do is we're going to factor what's in this set of parentheses, which factors to x plus 1 squared. It's always going to be a perfect square, so x plus 1 times x plus 1 is what this is right here. And then outside you get -6. So there you go. It is in vertex form. And so our vertex, let's just locate. That's what this thing is asking us to do. Complete the square and locate the vertex. Our vertex is at the HK values. So -1, -6. And then if we're asked to find the axis of symmetry, just note that the axis of symmetry is this x value in our vertex. So axis is at x equals -1. So there you go. Now we're going to graph this function here. So here I have it already typed out for us. And then also to get a really good idea of and a good sketch of what our graph looks like, what I'm going to have you do is, okay, we're going to complete the square, put it in vertex form, just like I have it here. And then whenever we find our vertex from putting it into this form, you can to find other points on the graph to help us in graphing it. This right here is our axis of symmetry. So for that axis of symmetry, what I'm going to tell you to do is pick 2 points that are to the left of that axis of symmetry, and then 2 points, 2 x values, that are to the right. Okay? And once you have that, plot those points, and you've got a really good sketch of your parabola, or your function of this thing. Okay, so let's graph it. Plot our vertex first, and then we're going to plot these other points. So -1, -6. It's right here. And then let's plot these other points. This right here is our axis of symmetry. That is where is going to be, that line right there is going to be where our function or our graph is symmetric, meaning whatever's on the right side is mirrored across to the left side. So like this right here, negative 3 is that y value of negative 2. And this point right here, 1, is just the mirror image across the axis of symmetry because it's at the y value of negative 2 also. So let's do that. Negative 2, negative 5. Let's look at that one first. Negative 2. Right there. And then across on the right side of that is the mirror image of it. And then negative 3, negative 2. See, across from the axis on the right side is going to be our mirror imaged point there. So we've got our points. Let's put them together. And there you have a decent looking graph of your function, your quadratic function. Okay guys, I'm going to show you another example of completing the square, but this time our value of a is not 1, it is 2. And whenever I say value of a, that means the coefficient on our x squared term. So first thing in the steps of completing the square is if your value of a is not 1, we have to factor it out. So let's factor it out. Take that 2 out, and we're left with x squared plus, and when we take out a 2 from here, take a 2 away from 1, we get 1/2. Then we're going to add a number here and subtract a number over here. But whenever we are factoring out a 2, make sure this number gets multiplied by whatever number is out here. Like I said, 2. We're going to multiply the number here by that same one. Okay, so what numbers go in the blank is we take our second term, 1/2, divided by 2, and then square it, which equals, inside it's 1/2 divided by 2, which is 1/4, and then squared is 1/16. So we're going to say plus 1/16, and then minus 2 times 1/16. And now let's just simplify it down a little bit. 2 here. And then just write this down. And then the number, the value that's on the outside here is negative or minus 6 minus 2 times 1/16. That all ends up adding to minus 49/8. You can plug this into your calculator and figure it out, and what I suggest is leave it in fraction form. Don't put these numbers in decimal form. Now let's factor what's inside our parentheses. And like I said, it's going to be, it's all what's in, whenever we complete the square, what's going to be inside these set of parentheses is always a perfect square. So in perfect squares, always just write your x term here, just 1x this time, and then take the square root of this value. That's what goes in here next. And then we're going to square it. Now, what sign is going to go here is always what is here. They're going to match. Okay? Now square 1/16, or take the square root of 1/16, sorry, and you get 1/4. Okay? Sorry. There. And then subtract your 49 over 8. And there you have it. That is your function, f of x, after completing the square. Now your vertex, let's go ahead and state that. Vertex is going to be negative 1/4 minus 49 over 8. And your axis of symmetry, or just your axis, is at x equals negative 1/4. Okay. Now, I'm going to skip this next part of graphing it. Maybe. Nah, let's just go ahead and graph this. So here we have that function in vertex form, and we're going to graph it. So very similar to how I graphed the previous one. You graph the axis of, well, you graph the vertex, and you notice where the axis of symmetry is. And mirror all of your points that's on one side to the other side. So where is this axis of symmetry? 1/4 negative 49 over 8. It's really close to negative 6. And then let's plot some other points. Negative 1 is at negative 5. Okay. And then let's graph some more. Negative 2, 0. Okay. Let's do the same thing on the right side of this thing. I'm just going to mirror it. Alright, now sketch your graph as best as you can. Okay, there we have our graph of our parabola after it's been put in vertex form. Okay, here is another way of finding your vertex, is this right here. Your axis of symmetry, or this h value, here's a formula for it. So if you don't have your function in this form right here, and it's in this one, what you can do is to find what h is use this formula. Say negative b over 2a, that will find your value of h. And then to find the value of k, take the value of h that you just found and plug it in back into your function and solve. So let's do an example of that. So this example is wanting us to find the vertex of the parabola and the axis of symmetry. So first, find the axis of symmetry. Where is that x value? Use that formula that I just told you to look at. So, need my pen tool. There it is. So at x equals negative b over 2a, and remember, this is going to be our a, and our b, and this is our c in a quadratic function. B is 12, so plug that in. A is negative 3, plug that in, and reduce this. So we get positive 2. Now that is our axis of symmetry. So axis is at x equals 2. And now our vertex is going to be at this x value, then whatever y value is after we plug in 2 for our x. So let's plug in 2 and evaluate this. Okay, if we evaluate that, we are going to get 4. So our vertex is at 2, 4. There you have it. That's using our vertex formula. The last thing we're going to look at is something called a quadratic model. And one of the quadratic models that we can look at is something that measures the height of a projectile. If you don't know what a projectile is, just think of a football player kicking a ball. It makes a curve just like a quadratic has. It goes up in the curve and then it goes back down to the ground. And that's what this particular model is it measures that height of a projectile, with our initial height being this right here, and then our initial velocity being this right here. So whenever you're given a quadratic model to write, or in a word problem, you will be given the initial velocity and the initial height of whatever the projectile is. And this number right here comes from gravity. It's going to be constant, and if your model is measuring things in feet, then this right here is going to be the number you put as your constant. And if you're measuring in meters, the number changes, and I think it's 4.9, I want to say, but your book will tell you that too. Okay, so here it says a ball is thrown directly upward from an initial height of 75 feet. So there we go, is our initial height. And initial velocity of 112 feet per second. Give the function that describes the height of the ball in terms of time. Our function is always going to be measured in terms of time. And remember, this formula right here, which I will give you on a quiz or a test. You don't have to remember that. But here, what we need to do to come up with the formula is, or the function that describes the height of the ball in terms of time, is plug in our initial height and our initial velocity into our formula given. So that's what I've already typed up for you right here. I plugged it in, initial velocity, initial height. There you go. There is our function that describes the height of a ball in terms of time. Now we're going to use this. Okay, after figuring out our function in terms of time, here are a couple of questions that we can be asked to apply after finding that. So what we're going to do is, it says, after how many seconds does the ball reach its maximum height? We're going to find that. And then also, what is the maximum height? We're going to find that one too. And that all revolves around where is the vertex of this parabola. So the maximum height is found at the vertex, which makes sense. It's going to be the highest point on that parabola if we were to graph our function. So looking back at our function that we just stated in the previous slide, sorry, not f of x, it's going to be s of t equals, let's see, negative 16 t squared, 112t plus 75. To find how many seconds does the ball reach after its maximum height, we just need to find that h value with the formula that we used, the negative b over 2a, which actually I want to call this our t value to go along with our terms of time that this function has. Okay, so negative b is negative 112 over 2a. A is negative 16. Reduce that, you get 3.5. So that answers our question. For how many seconds does the ball reach after its maximum height? It's 3.5 seconds. And then once we find the time that's passed by for the ball to reach its maximum height, we can take that time right there, the 3.5, plug it back into our function, this right here, and solve that, or evaluate this, and once we evaluate it, that is going to give us our maximum height. So that is 127, and since we're measuring things in feet, the units of measurement here are feet also. There you go. So the ball reaches its maximum height at 271 feet after 3.5 seconds. And there is our model. And you will have a couple of questions just like this in the work that we do in the class. So if you have any problems, that's what I'm there for. And I will see you all in class. Goodbye, everybody.